Welcome, everyone. It's always a pleasure to host talks at GTC. In fact, this is my second one at this show. And some of what we'll be covering today was discussed in my previous talk, which was actually much shorter than this one. And I wanted to take the time to introduce those who don't know about OTOY to what we do and share with you our work on something that is really fascinating, which is a blockchain application for ray tracing. And ray tracing has been a really hot topic, obviously, since GTC and since ray tracing has been now become almost standardized in things like DirectX and Vulkan. And there's just a lot of optimism around reality becoming much more tractable. And Render, which is the project that I'm here to discuss with you today, is really our software stack and service and ecosystem around solving the problems that we think are going to be important for creators and consumers in the 2020s, in the next decade. And I think that as we end up 2 years out from now, things that we consider to be expensive and hard and impossible, like perfect photorealism, are going to be commoditized. They will be free, and it's nice to see things like RTX and DirectX ray tracing start to make the case for that. Everything is going to be real time. I think the idea of having tools and applications where there's even an offline render mode or wait are going to go away, and you're seeing game engines now like Unity and Unreal driving graphics for cinematic tools, and you see film directors like Neil Blomkamp that are doing amazing work in Unity. And I also think that the tools of the future are not going to be driven with a tablet or a mouse. They'll be intuitive, and I think that means that you'll have touch input, there'll be spatial, things like tilt brush and quill and painting tools that I think Adobe showed at SIGGRAPH last year that are all in 3D and volumetric are probably going to be something that users of all skill sets will be able to apply and not have to worry so much about the technical semantics of the tools. That's going to be great. I think it'll be a big democratizing force, and we're just seeing this already happen even ahead of the next decade. And we're seeing, a lot of interesting things happen, especially in that last layer with ARKit and ARCore, using phones as portals and windows into mixed reality. And that's a big part of why Render is so important, because publishing and creating content in this emerging ecosystem is not all figured out yet. So our mission as a company, we're about 80-something people now, is to democratize what we think are going to be the tools and the services that are hard but important in the ecosystem that we want to see happen in the next few years. And we've been talking about the work that we've been doing now for over 10 years, and we've been dividing this sort of holographic ecosystem, because I do think that beyond mixed reality and AR and VR, you're going to get to light field displays. The holodeck, the Star Trek holodeck, is literally not that far off, in my opinion. And as a company, we've actually had 3 divisions: Lightstage around capturing reality, and Octane Render, which is probably what we're best known for, which is a GPU path tracer that delivers beautiful cinematic content. You've probably seen it on TV, instantly. And then finally, we've been working on streaming and delivering holographic content through open standards, which we've been pushing through things like MPEG, and we've developed that as Orbex, and we have media players that are on mobile devices and VR devices that allow you to stream and play back content in VR and eventually holographic devices and displays as well. So I'll start with Octane. For those that haven't seen Octane, this is what it renders. This is the opening of Westworld. A lot of my favorite shows have actually been rendered in Octane, and Octane's available for many different tools. This is done in Cinema 4D. This is The Crown on Netflix. And it's so fast that really you don't need render farms for doing production-ready work in film and television like this. You can do that on a few GPUs or a small rack in an office, and it's awesome. And I'm really proud that Octane has been able to deliver these results. When we started Octane 10 years ago, it was not clear that GPU rendering was going to be production-ready. CPU, RAM limits, all these things were factors that really were in our way, but we've solved almost all of them. And today, or actually as of last year, Octane is now available for free inside of Unity Editor, and we're very proud of that relationship and that partnership. What that means is that all of those graphics, those cinematic renders that you saw being done on just off-the-shelf GPUs, sometimes really high-end GPUs from NVIDIA, but either way, they're tractable pieces of hardware. You know, all the millions of Unity users now have this renderer for free, and they can bring in assets from other tools, or they can create it all in Unity. But we're convinced that this is a big part of the future. So democratizing cinematic rendering on GPUs, big part of our stack. But really, where we see the future, and it is something that anyone who's developed in Unity or Unreal or game engines might be familiar with, until we get to completely real-time holographic live rendering, we want to pre-compute things if we can. And so we've developed technology around baking light fields and holographic images and textures and volumes so that we can sort of cheat and get to perfect fidelity on today's AR and VR devices. And we're going to bring that to Unity this year, and to also many other tools that are not necessarily game engines, but still important for creators and publishers of content. We also last year announced a partnership with Facebook on cameras, specifically volumetric 6-dot video. There was a camera system that they developed with 24 lenses, which generates a really awesome light field, and we'll get into the capture pipeline that culminated in that here. So we actually started our work on reality capture at the very high end with LightStage, which is a really high-end device that came out of work at USC and is now used for almost every major motion picture to capture digital doubles, human skin. And even the President of the United States, this is our first portable light stage. So this is really sort of showing the history of how light stage is applied. And unlike traditional depth and color capture, the process we get from light stage actually captures everything. It captures material properties, what you need to get skin to look good. And this is an example of almost really an early light stage test where there's so many lighting conditions that you could re-render this head perfectly from a light probe. So imagine this in mixed reality. That's the data that light stage gives you. You don't have to write shaders. You don't have to figure this out. This is not a photo. This is an actual render from all the different lighting conditions that are captured with light stage. And we've been steadily improving the quality. This is a test from, I guess, a few years after that, where we were getting information around, strands of hair and doing that in motion. We got that to be much cheaper. This was only a couple of years back, where we were able to do a test with just 2 cameras and then bring the data inside of Unity, where we can relight it, do it live. So this kind of capture is really important. I mean, in order to get to a reality where mixed reality is fundamental, you have to be able to know what the real world looks like and be able to deliver that in real time. And even for artists, it's a huge time saver to be able to use light stage technology. And we're trying to get this into tablets and phones. We only need 2 cameras that are running 120 hertz and 4 lights. And you just get back awesome details that you can then drop into a CG render like Octane. So a little bit later, I'll be showing how that works end to end for capturing something on the light stage or something along those lines, and then running it through our ecosystem of software and services, and then delivering that to an AR device. And it's also been used in the assets you can see in Unreal Engine. The assets that were released for Paragon actually were from LightStage. We can use it for material capture. And in fact, we did a contest with Oculus a few years back where photogrammetry was a big part of one of the contestants' entries. And he went to Japan, and he lived in Japan actually. This is a real place, and he scanned it in with photos and built the scene in Octane, and actually won, I think, first prize for one of the months. It's beautiful and it's amazing. And so capturing reality live is really the next stage. We did tests with depth capture. We've also experimented, probably very famously, with doing true, hardcore brute force light field capture. And the very first test of that was just spinning a camera around and getting thousands and thousands of views, and then turning that into a spherical light field. And the team that did this with us, that included Paul Debevic, Greg Downing, they actually just recreated this test for Google, and you can try it now on the Vive. It's called Welcome to Light Fields, and this was really sort of the precursor to that. Our work with Facebook, though, was really much more about the practical applications of how to do capture, and 6-dot capture in particular. And we're very proud of that work. I mean, you can go see their booths, and you can see that we're really right in the middle of that ecosystem, and integrated in many video tools where you can just take the data from these cameras, work with them. It's a lot lighter weight than those heavy light fields, but the results look really good. And our commitment really has been to bring this to a suite of tools like Unity, After Effects, and Nuke, and allow you to play with both the capture, rendering, and publishing process. And the results are cool. Like, this was one of the very first tests that was done with the Facebook camera. We brought it into Nuke. We added a CG asset. The background, I think this is on the roof of Facebook. And you can then even bring that into a game engine like Unity and drop in interactive assets and lights, which are pretty cool. And for F8 last year, we showed this demo where I was able to take put a light source on the Rift controller and actually relight the scene as you're watching this volumetric video playback. So there's definitely another layer and leg to all this work, but this past year has actually been really fascinating on the capture side. For rendering, which is the second leg of this workflow, everything is really built around having a standardized set of assets for what you want to render, and that's what Orbex has been all about. It's very much like the document object model for the web or HTML. And in fact, this is what an Orbex file looks like. You see an object, it's rendered, you have a scene graph, and it's built around existing open standards like Alembic and Open Shader Language. But it's actually, no one's ever actually gone all the way and built something that is a self-contained packaged scene file that has everything you need to render. And we import and export Orbex from 26 different tools, including Photoshop and Houdini and After Effects, Unity, and the list goes on. It's a huge ecosystem, and most of that is free now. And it also supports things that are not typically in mesh formats, like, for example, OpenVDB, which is used for volumetrics, Open Shader Language, which we have compiling on GPUs to do procedurals, which are really useful and fundamental. And essentially in that node system, in this XML that is basically the equivalent of HTML for Orbex, you have the ability to write shaders and even create procedural effects. So our goal really with the ecosystem around rendering has spanned almost 10 years now, and Octane as a product has provided really millions of users with what GPU rendering can do. And Octane is unbiased. It actually follows the laws of physics, very important if you're going to get to the holodeck at some point. And every 2 years we had a major release, and Octane 1.0 was really mostly targeting stills and architectural rendering. Version 2, which came out in 2014, added motion blur, and you could do animations. And then by version 3, which was released in 2016, we were at the point where we had production-ready cinematic GPU rendering. And all of those shows and those cinematic effects I showed earlier were done with Octane 3. And just a week ago, we released Octane 4, and the focus of Octane 4 is to keep everything in the cinematic pipeline that we had before, but make it all real-time on GPUs, target game engines. And along the way, we discovered that AI was actually an enormous boost to getting speed and quality. And as we head towards 2020, where we know that light field and holographic displays, and even in fact the entire media formats around those kinds of displays are going to matter, we need everything that came before that, because we're going to be dealing with a lot more rays and a lot more rendering power to target something like the holodeck. So Octane 4 is a great release. The build is available for download now for Windows, and the plugins for all our tools will be released shortly. But one of the exciting integrations is inside of Unity. Inside of Unity, you can already import Orbex files that are exported from any of the other tools. So if you like those cinematic openings you saw, you can actually take those, that opening from an HBO show and drop it in Unity and treat it like a game asset, which is really cool. And you can then use that to bake the lighting from Octane into a mesh, which is typically what Unity does for existing assets. But having this work as a simple one-click drag and drop for free is a big game changer, and it introduces the concept of being able to access a huge production-ready pipeline inside of the tool that's used for most AR content today, which is Unity. So you have parity. We can even turn our cinematic scenes into Unity materials, and baking is obviously accelerated on the GPU. It's very fast. We're also seeing baking being very useful for things like Sketchfab or Facebook 3D Posts. We're supporting GLTF, but that really begins with providing this as a system in Unity. And it's great that Unity is free. It just gives everyone a leg up and a great tool set to get started. And as we go into this year, we're really working closely with Unity to make sure that the cinematic material system from Octane is reflected in the HD scriptable rendering pipeline, which is being added in Unity 2018. And we even have game mode working in Octane 4. So you can actually run Unity games and path trace them, which is what you're seeing on the left. Still very early, but it's very promising. What we want to do is we want to give people everything that they need to build games of the future that have Octane quality. And so I want to get into Octane 4 and what it adds to make that happen. We've actually, first of all, we actually added a whole new pricing model to make these tools accessible to more people. So we've upped everyone's licenses. Existing Octane users that bought the box license, they have an enterprise version that can support hundreds of GPUs. We have a $20 a month subscription that gives you just about everything you need in Octane today, including all DCC plugins. And then the free GPU version that's been in Unity since last year now supports 2 GPUs, and we're going to be adding even more plugins to that free tier. And so the subscriptions for $20 a month really give you a ton of stuff. They give you a second node license. You can basically use network rendering, again, access to these 25 tools, and we're also giving cloud access. So in other words, if you don't have enough GPU power, you can send your scenes to the cloud, and we're providing the OB per hour as a metric for ray tracing, and that's a big part of Render's stack. And we're also letting people just add extra nodes for $10 a month. Enterprise licenses, 200 GPUs. That's something that maybe a data center could use, but we support it. USB key for offline mode, again, for productions that wanted that. And NVLink, which allows you to combine the GPU memory on high-end cards. That is part of the enterprise tier in Octane 4. Now, the free tier is really interesting because obviously, we're a commercial entity and we want to make money, but this is a long-term bet. It basically means that we're giving a huge part of what we actually had made good money on with Octane away for free because there's no watermark. You can use it for commercial use. But the idea is that it allows people to connect to this larger ecosystem, and it gives us the opportunity to add services and get people to be subscribers or to buy Octane as we continue to improve the entire stack. So with that in mind, we wanted to have an amazing release with Octane 4. And a lot of people have been asking us about a technology that we've been showing for many years called Brigade. Brigade is now built into Octane. We were able to merge these things together. For those who aren't familiar with Brigade, we actually showed this demo at GTC in 2015, and it was running on 80 GPUs on the cloud. And what you're seeing here is fully path traced rendering, not ray traced with reflections. The whole thing is basically running as a path tracer in real time, no noise, and it's beautiful. It requires today probably the equivalent of 16 Volta cards. As it turns out, that's exactly what's in the new system that Jensen showed, and that's awesome. But in order to leverage Brigade, it was actually a lot of work to try to integrate that inside of Octane. Brigade was designed specifically as a game engine, so you can do bullet physics in real time. You can treat it very much like a video game. There's no wait time. There's no latency in there. And merging that into Octane, where the latency was actually pretty high, took a lot of work. It took years, but it's done. And the results are pretty awesome. So in Octane 3 on the left, moving a giant mesh takes about a second to recompile the scene. Octane 4, it's like 1 millisecond. So you can just move things around at 60 frames a second. All you have to worry about in Octane 4 is the noise. But it's just a game changer. I mean, when you are an artist, or even imagine a game rendering with perfect Octane graphics, being able to change anything and having that change be at zero cost is awesome. And it just removes one of the big problems that we knew we had to deal with, which was how do we make sure that we get the holodeck to be completely dynamic and to not have to bake or pre-compute anything. And this is an important step. So we're really excited that Octane Scene Graph now has Brigade in it, and that we're able to deliver this incredible performance. It works with deformable objects as well. You can now load in FBX and Alembic files, and those can be scrubbed and displayed in real time. And it's a game changer for a number of reasons. Brigade integration really allowed us to rebuild all of Octane and fix some problems that are really just hard problems. We can now support out-of-core geometry. That means that we can load in giant scenes that are completely in system memory, even if you run out of GPU memory, and it's still fast. And to sort of test this out in Octane 4, we started with the worst case scenario, which is nothing is in GPU memory. This is 0K of VRAM, and you're still able to move about 40 gigs of out-of-core geometry at 60 frames a second interactively. That's the worst case scenario, which is pretty great. We also tested that across 2 GPUs. So Octane is twice as fast on 2 GPUs, 100 times faster on 100 over network rendering, and it works even when you have out-of-core entirely in CPU memory. And then we went on to Amazon, where we had 8 Volta cards, and that also worked, and we tried it with 150 gigabytes of scene geometry. So we're at the point now where there's nothing that goes into a film that there's no excuse for CPU rendering. Octane is able to support it all, and it scales awesomely. And there's a lot of performance improvements we're seeing on Volta, so that's fantastic. Now, in order to make this work well, when you have part of the scene data on the GPU and off of it, we've introduced a new feature called Scene AI. In certain cases, the speed is the same, whether it's out of core or in core, because of how we cache the rays. And yet when we move the camera or something happens, it all breaks. So it's fragile, but we've been able to actually map the topology and create a heuristic that is able to basically solve that problem. And we're seeing now, and our users are sort of reflecting that in a lot of cases we can actually gain most of our speed back. And so out of core, especially if it's just a little bit of extra, a few gigs extra, doesn't really slow the engine down. And so there's a lot of AI features that we've announced in Octane 4 that are just game changers. The second one after AI Scene is AI Light. And AI Light is something that was an experimental feature that we weren't sure we were going to ship. What it does is it solves one of the hardest problems in true unbiased path tracing, which is when you have a tiny little point light or a spotlight, it's very hard to find where that is if you're just shooting rays randomly, which is how the rendering equation works. AI lighting gives hints to the renderer about where those things are, and in the same rays, this is I think 8 rays on the left and the right, you get a much faster, cleaner image. It's not a denoiser, it doesn't run as a post-processor, this is in the renderer, and yet it also doesn't break the unbiased physical laws of light that Octane follows. It just solves the rendering equation much faster. So if you just let it render, you'd always end up with a clean image, but if you see on the right, 200 samples with AI lighting on is way better than with it off. And if you're doing this in real time, you only have 2 samples, the number of those 2 samples are basically figuring out where the light is much faster. And so this is awesome. I mean, now we basically can, in real time, even if we have just 8 samples, which is what this is showing, with AI lighting on, we just have to denoise a little bit. And that's awesome because with a denoiser and this technology, we now have the pieces we need to get rid of that grain and that noise and leverage the fact that we want to get to real time with Octane and Brigade. So the last piece of that is the AI denoiser that we built. Specifically, this is targeting really high-end final frame rendering. It's deep in the engine. We're going to be adding the optics AI denoiser as well, but this first piece is specifically targeting non-real time, although it does work in the viewport. So this is the denoiser in action. It takes about a second to denoise the frame, but as you can see here, it works for things like glass and skin and all these things. And when you combine that with AI lighting, the results are awesome. Because what we found is that the denoiser, if we train it with AI lighting, it actually is able to figure out, with even those few samples, how to finish the rendering. And I was skeptical 2 years ago before we really invested all this work into AI, whether it would all work and it would help, but it does. I mean, now we're at the point where a 1-second render is replacing a 5-minute render. 50 samples versus 3,000, which is what this scene required. And you can see the denoiser, once I'm done moving the camera, it takes about a second to render, and then it's a split second to denoise. And the results are beautiful. This is a game changer for people that are using Octane for offline rendering, but it is clearly an important aspect of supporting Octane quality in real time. If we didn't have AI and AI lighting and all these other things, we'd be completely dependent on just ray tracing speed getting faster. And even if we were to accelerate that by 10 or 20, it still wouldn't get us a noise-free image, which is why these pieces are so important. Combining all these things together is pretty exciting. So these results are they're just magical. And I'm very proud of, especially when you're looking at refractions or reflections, the AI knows it has enough information to figure out what's noise and what isn't, and you just end up with something that really does, to me, prove that AI can actually be leveraged with results that are production ready, and it's not this blurry kind of thing that actually is great for previews but isn't ready to be shipped. I think there's still so much more we could do with AI, but this is already great to have in users' hands. We're also adding some other features in Octane that really get us closer to covering all the different laws of physics and light. So we're adding to Open Shader Language support for atmospheric shaders, planet shaders, which is really cool. You can do space stuff now. And then we have some other features we're going to be shipping in the final version. Newer material, better deep pixel support, better subsurface scattering, and asset compression. We are also going to be updating the speed at which we push out major releases of Octane. So the next release after Octane 4 is Octane 2018, and we're going to be probably doing away with these version numbers and just going to 2018.1 and 2. And in the next version, we're adding light linking, better support for Houdini, and just adding basically from the forums and user requests what users want, and updating Octane fairly regularly from this point onwards. AI is going to continue to be fundamentally important to what we do in Octane. There's so much more that we see being added as far as being able to track people, faces, turn that into stuff in real time. And we have a lot of these pieces between Lightstage and Octane and all these other things that just make me feel confident in the fact that we're going to have a lot of creative tools simplified by AI, not just in the rendering stack, but just in the utility. And you see that work already happening in 2D and in video, but we're seeing that also as a real possibility in turning the real world into cinematic CG assets and scenes. Lastly, on the render side, I want to talk about our cloud service, Auric. We launched it in 2015. Our users use it to render typically animations, but a lot of users need it for VR rendering. As fast as Octane is, when you're going into 50 megapixels per frame for 10K VR render, you want to have a lot more GPUs. And so we built a service that's built into all of the Octane plugins. There's a web front end. You can hit a button and just finish your render on the cloud. And since 2015, we've basically simplified the service. It's built into Octane. You can buy credits for $5 that are mapped to Octane Bench, and usually you're getting a one-day turnaround, and you're seen in any of the tools are synchronized with the cloud service. So it's really straightforward to use, but we want to improve that further. And Render, as an ecosystem, is designed to help figure those pieces out. In fact, one of the things that we're using the cloud for beyond rendering is processing Facebook video data, this is from one of their slides at F8. We actually take this data from their camera, we process it in the cloud, and then we provide an ORBX that's generated from data back into these tools. And then the other side of that is we actually also help deliver the media itself. And that could be 360 or 6DoF, and that's where streaming comes in. So this was another slide from F8, and it shows the different formats that we are responsible for delivering at the end of that last slide that you saw. And some of this is existing stuff, just 360 video, MP4, you drop that into your newsfeed. Other formats are similar to what we put out on the Gear VR, where we had these really high quality 360 stereo cube maps, 18K. More recently, we've been working on a 6DoF version of that you can run on the Rift, and that's similar to what you were seeing in that Facebook camera demo. And then lastly, we have this very high quality version that is a baked light field, and that doesn't need any download, it's just a live stream. And light fields are awesome. So this is basically our hedge against not needing all this crazy rendering power. If we pre-compute every possible ray of light and turn it into a hologram and store that in a texture, then we end up with essentially a free path traced view that can be looked at from any angle. And we showed this at SIGGRAPH in 2014, and people were really excited by that. We kept building on that work, and we ended up building a version that could actually render an entire volume, a cube, which is what you're seeing here. This is all out of Octane. Those jobs are done on the cloud. They can be very expensive, but it works. And we also made sure that we could stream it. So this is one frame of animation and 1 meter in the z-axis down that street, and it streams and it's perfect. And genuinely, you're seeing the 6 walls of the holodeck in this embodiment. And so for us, streaming holographic content is definitely important. It solves a lot of problems. We can also merge synthetic holographic content, light field content, with what we capture from the Facebook camera, which is what we're showing here, and we can stream it. And in the case of AR, it's actually not a heavy stream. We run the light field viewer on the cloud. The phone, if it can track itself, can basically send the portal to the cloud, just what the rectangle is, and then we just send down this live stream. And the latency is actually really good, even over LTE. So the ecosystem around how to leverage this is also important. It's not just getting streaming to work. We want to have this work in the web. We want an open metaverse. We've tried all these different approaches with usually Facebook as a partner. We embedded ORBX streaming into Oculus Social, Oculus 360, Samsung Internet. And in the case of Samsung Internet, I think you can even try some of these things live. We also enabled you to build even take your Unity projects and embed them in an ORBX package. And this is actually running an entire Unity runtime native performance inside of an ORBX file. And it's cool because there's still things missing in WebGL and WebAssembly that aren't solved, and we still need that performance on mobile. So getting Unity to games and interactivity to be part of the media stream is pretty nice. And that takes us all the way back to what we're trying to do as an ecosystem partner. And if you combine all of the things that we've shown together, that's this year's focus. And for the first time, I can actually say that really rather than 3 parts of the company, we've got one one continuous service, and that is render. And we need that for mixed reality. There's a lot of things that we can't solve in one of those layers that get solved by combining all of them together. And a big part of what we did last year was introducing a blockchain-backed token called Render Token. And every service, every single ray that goes through our system, whether it's captured, processed, it all has a token that can back it. And we had an immediate and important use case to solve, which is ORC. So ORC, one job could actually bring Amazon to its knees, and that's okay. I mean, Amazon's aware of these problems. They are our partner. But it's very hard for us to build a service where we probably need hundreds of thousands or millions of GPUs to support all the customers that could possibly be rendering with our stack. And we haven't really turned on things like light field baking and even processing volumetric video because we're scared that we don't have enough GPUs. So the idea of render was that if we can turn all those GPU mining cards that are out there, and there's a lot, I mean, there are millions, into nodes that could fulfill work that when we run out of nodes on Amazon, those people that are running those nodes will actually make more money than they would mining Ethereum. And that actually got a lot of people excited, including us, because now if we do get that kind of capacity, finally we can start to really seriously offer through our stack jobs that are going to be important for the 2020s. Whether it's rendering or streaming high capacity holographic content. And we actually have done a lot of work already. There's a 4-phase process that we committed to doing since we launched Render Token in October. Today we actually have phase 1 working. You can actually take the tokens from our token cell. You can pay for rendering work on ORC, and we can actually render, instead of using Amazon nodes, we set up a data center ourselves to test a decentralized version, and it actually fulfills the jobs. Since November, a certain number of them have actually been done off the public cloud. And we have more work to do. We need to launch a system tray that lets everyone render scenes, not just us. We need to do that securely. We need to add the proof of work as a watermarking system that is not on the current version of our system, but it's an awesome system. And the render token itself actually is based on 256 octane bench times 256 seconds. Today, it's roughly about a kilowatt minute of GPU ray tracing power, but it's absolutely an amazing economy. And I actually thought of the idea of having some sort of tokenized ray tracing system 10 years ago. It's really it's amazing the things you can build with that as a fundamental unit of energy or value in the system itself. And then I think once we solve these earlier problems, then phase 4 is where things get interesting. That starts the end of this year. So we already have so much information in the render jobs themselves. We know who's creating what. We actually track every asset we have to. That's the only way we can do delta syncing. So we can actually start to add layers. If you want to add an extra render token cost to your asset being used or reused or remixed, you can do that. And the blockchain will back that. And it's amazing to sort of think of what having an immutable ledger can do when you get into publishing, as well as the more immediate things that we're solving through actually doing real work. And another part of phase 4 is going to be real time. We imagine a day where streaming and rendering will be one and the same, live streaming, and we'll need that for holographic displays and shared metaverses. I think the true value of a blockchain system is not in hashing numbers, but in hashing scene graphs and rendering that you would share. I want to make sure I'm doing okay on time. And then a big part of making this work is not just putting out tools and services, but also having an SDK that lets others build on the core pieces that we're already launching ourselves. So having a render SDK that targets what you can do with Octane is our first step. We're internally using that, and the SDK actually has access to Brigade Engines API, the Orbex importer and exporter Octane rendering API. Our light field streaming and codec stuff is in there. And we also are adding things called AI Viewport, which is designed for thin clients that need to reproject light fields. And then, of course, you have access to looking up resources that are on the blockchain to pull down an Orbex file or a service or a module built in the SDK. And this SDK is the future of our company. So we've been building everything in Octane on CUDA. We've done our own GPU compilers, but going forward, even Octane is going to be rebuilt on the Render SDK, and there's a lot of value that comes from that. So pieces of Octane also will move to the blockchain. Things like LiveDB, of course, the cloud service, the rendering piece. But so far, we have these backends that allow us to take things that are built on the Render SDK and spit out binaries for CUDA x86 CPU, Vulkan, Direct3D, and Metal. And with about 40% of Octane already on that stack, and we are also going to be optimizing for RTX that's in the new Volta cards, we can now look at a whole new set of devices that we can support with Octane and with render jobs. So we now have integrated graphics on Intel supported, and you can see here it's running scene from Octane Bench. This is the AO part of the Direct Lighting kernel on a MacBook. It's maybe 30-ish Octane Bench, not too bad. This is the same exact Metal Octane version running on iPhone and iPad, and the crazy part is a 10.5-inch A10X is faster than the integrated graphics on the MacBook. So, if we ever turned on render jobs for somebody was applauding for MacBooks and those millions of Intel processors, your iPad is going to probably do just as well. The only problem is you only have 4 gigs of memory on these devices, but then again, I think there's only 4 gigs on my MacBook as well. And we're seeing probably something that we already knew, which is that the integrated graphics parts of the Intel CPUs are so much faster that it doesn't make any sense to do CPU rendering. So if we ever had a CPU fallback, it would just be using the Intel integrated graphics. And yeah, it's crazy to see iPhone and iPad beat a laptop, but that's the world that we're living in. So the front end to this system is GLSL. That's what we're actually using to build most of these pieces, but it's GLSL compute. You can do everything you can do in OpenCL and more. It's simpler than CUDA. It doesn't have all those things that you might want, but it is much easier to perform cross-compilation. And when you basically create a module in, with this code, it turns it into an ORBX file and it's published on the blockchain. It gets pulled down. And so eventually all of Octane, all these services are just going to be packages that are backed by the Render blockchain. And we actually expect people to build new renders. Between Brigade and Octane and those two APIs, there's all sorts of things that can be done creatively, and we want people to invent and come up with totally new things. So for mixed reality, all these pieces together, really important. Going back to that earlier slide, that Disney asset on the left that we light staged, and on the right, which is streaming into Tango phone. How this works when you're, for example, doing this within Unity is you can take an asset, send it to the cloud, it gets turned into a light field, it can be streamed back. This is also showing the streaming after the rendering is done inside of your Unity project, and then you publish that. Again, you publish that Unity project, and an AR phone like the Tango in this case, or AR kit, can consume it, and you can place that in the real world, and that could be stored on the blockchain, which is pretty cool. Now, as far as mixing light fields together, because that's all we're going to have until we get to real-time path tracing, it works. This is also in Unity Editor, and I'm taking 2 pre-computed light fields. One of those was the cube that I showed earlier, and I'm blending them together. And we're actually still doing ray tracing, but a lot less. So we actually are just handling reflections and shadows, and we're saving a lot of time. So this makes something like the iPad a tractable mixed reality device, which is important, because to support ARKit mixed reality, we need to be able to capture the scene using the back-facing cameras, a stereo camera to depth, turn that into essentially a 3D model on the fly, which is what we're testing here on the iPad. This is running at 120 hertz. And then, once we have that working and we have a rough sense of the scene, we can then start to do really cool stuff in mixed reality and bring in light fill streams or other objects and essentially do minimal amounts of ray tracing and path tracing. And maybe one day there isn't going to be no light field or pre-computation necessary, but these pieces running on today's phones are really important. Beyond that, light field display walls are going to be amazing. And I started to test how that would work late last year using an iPhone 10 to track my face and turning on our light field viewer on a monitor. And everything's being tracked with a Vive tracker. So I'm having the experience in one eye of seeing a light field without any glasses, without wearing anything, using just a commodity phone to basically send, and the latency was really good, my face, my eye position to the server and beam a light field down. And it's pretty great. I mean, I have to say that as much as I believe in the future of AR glasses and VR, I think it's going to be much better when you don't have to wear anything at all, or you can have, like this, I'm showing here, I'm turning the monitor, it also is able to reproject a light field, so everything's being tracked, my face, the phone, the display, and this probably indicates how things will really work. I mean, you're not going to have to wear glasses or put on goggles to be in mixed reality with true holographic displays that are coming out. That'll also make this work on the thin devices. The last piece of the Render SDK that I want to sort of go into is the AI Viewport. And the goal there is that no matter what we get, if it's even just a few views or it's part of a light field, we can rebuild the rest of that light field very quickly, very easily. And that wasn't what we used to do. Those earlier light fields were brute force. It was still efficiently rendered and stored. But just rendering a few views, this is I think 6 views. You're seeing there's a lot of ghosting. That's a naive light field render, even with depth information. But with AI Viewport, those same views, it's magical. It just looks beautiful. There's no depth information, by the way. This is just essentially what is spit out by running it through the AI Viewport algorithm, and you can go into the scene. I mean, there's no depth, and it still looks beautiful. You get perfect, really nice edges. And then, of course, the other part that is important to interpolate is getting this to room scale. So this is showing a very small light field sliver, and then we can blow that up with the AI Viewport, and you actually have a light field for parts that are you can walk through. And we're saving 100x in bandwidth. It looks beautiful and awesome, and we're just at the very beginning of that. Next steps are also going to be using the AI Viewport to do super resolution, which looks pretty good so far, and of course denoising. And I think with the last few minutes I have, I want to talk a little bit about our efforts to be good stewards in what we want to see in a truly open metaverse. So we've contributed Orbex to MPEG. Cable Labs brought us in to the MPEG working group. I'm now officially an MPEG member, and we've actually seen a lot of interesting sort of partners change their minds around how light field standards and volumetric standards should be considered. I don't think that you need a light field format specifically. You need to start with something like Orbex that defines the scene. That is the ground truth. And it took me about 4 MPEG meetings to sort of start to see people understand that and get traction from that. Because if you have that as your mezzanine format, then you can generate light fields. You can have a target for cameras that are capturing reality to rectify against. And it's pretty cool that we're at the point where we actually have partners like Cable Labs that are basically pushing for this. And what I want to see happen in the 2020s is no more siloed verticals, whether it's apps or even web pages. I mean, we should be able to mix things together in mixed reality. There should be no barriers. We should be able to create services and ecosystems. And I think that when you're talking about something that is fundamentally glued to your eyeballs, one way or another, that there should be a layer that isn't controlled by a single entity. And we're seeing a lot of angst around privacy and issues with what happened with Facebook and Cambridge Analytica. And so my sense is that having a layer that is protected by the blockchain in an open metaverse, really important. You can still build services and proprietary pieces above that layer, but I would never want to have my eyeballs glued to something that is owned and responsible by only one entity. I think that is dangerous, even if that entity doesn't want to do something wrong. So I'm excited for the future. We have some amazing partnerships. I mean, J.J. Abrams came on board as an advisor, Octane Maya user, and shares the vision that I do around all this stuff. And we want to just expose all this technology to the world, and this year is a big part of that. So I think I'm a few minutes left. Thank you, everyone. I don't know if you have time for questions.